Hey, welcome everybody. Thank you for joining the 2026 Action Team webinar series. Of course, this is the series leading up to CSAT. CSAT this year being June 9th through June 11th in Worcester. Very much looking forward to seeing all of you there. My name is Brad Richards. I'm co-founder and CEO of Powders on Demand. And today I am once again very excited to host Steve Camilleri from SPEED3D. And Steve is going to be discussing cold spray automation in action, and I'm sure he'll give you more detail there. He'll also give you a nice little live demo and walk through some of Speed's automated systems, talking about software and the functionality of software incorporation into cold spray manufacturing processes. So we do encourage Q&A throughout here. I have a couple of advanced questions that came through. I'm certainly going to have a bunch of my own questions again, Steve, but I'll favor the audience instead of my own great insights. And the recording of this presentation will, of course, be available to everyone after the fact. So for those of you who don't know Steve, somehow, if you don't, Steve is the CTO of SPEE3D, which is an Australian producer of cold spray 3D printing equipment. Also do a lot of work on processes and materials. Steve's got a whole bunch of patents. He has a master's degree. And if you can't tell, he is, of course, a masochist. He is actually going after his PhD. Aaron and I offered to transfer ours over to him, but he said they're not good enough. So he's decided to go and do one on his own. Prior to
Yeah,
founding Speed, he was a co-founder in Motion Technologies and kind of worked his way through a bunch of technical engineering disciplines. So, Steve, I'm not going to go on him for 5 more minutes. I'll let you add in anything you want here. And very, very excited to see your presentation. Kick it off, my friend.
thanks, Brad. Really appreciate that. All right. Yeah, welcome everyone. Thanks for that wonderful introduction. So, yeah, Stephen Camilleri, CTO of Speed3D and co-founder. So, looking forward to seeing you all at CSAT. I'll be there when it happens. So, I was asked to put together a bit of a brief on what we do with automation. So, some people kind of know what we do well, some people don't. So we do cold spray, yes, but really the headline act in our little show is the automation. So what's automation in cold spray? I've done a wonderful image here of a very smug-looking robot holding a cold spray gun, and very happy that he's just made this gearbox housing. That, of course, is not how it works. But I wanted to have a nice image on the main page. So let's get into the real presentation. So, a bit about us. We've been around since 2014. Some of you know me, some of you know Byron Kennedy, my business partner, co-founder. So this is a bit of a brag slide. There's lots of famous people on this slide. We do a lot of work with the different defense forces around the world, and we put our equipment in the field and we solve problems in the field, which I'll talk a little bit about today using cold spray. So we didn't start in cold spray. We started somewhere totally different. So I've got some pictures here of where we actually started. So Speed3D is our second company together for Byron and I. The first one was in electric motors. So this is a technology that came out of our work, with solar cars, solar powered racing cars, where we had a world record for a little while. So what you see here is a swimming pool pump motor, which is boring, but includes in that swimming pump motor a very fancy permanent magnet motor, which is derived from the back wheel of our solar car motor. We shrunk it down, commercialized it. It's in production. We built the production facilities ourselves. So, in short, we were tech guys that got bought out by a large manufacturing organization based out of Wisconsin, Indiana, in the US. And we went to work for them. They taught us how to do production. They made us set up the factories for these electric motors, which was an absolutely wonderful experience for tech people to be learning about manufacturing. And so this is our background, was this pump motor, which reduces your swimming pool power consumption by 80%. It's actually a huge saving, enormous amounts of cost reduction for that new technology. It's kind of changed the world in swimming pool pumps, which is the saddest brag you can imagine. But there you go. So here are the problems that we knew in that industry. So there's a large, it's called an integral horsepower motor. So if you've ever been in a pump room or an elevator room, you've probably seen something like this. Very standard technology called an induction motor, invented by Nikola Tesla a long time ago. So those motors include a lot of cast materials. So by that we mean we take a molten metal, we pour it into a hollow, we let it solidify, and we pull the part out shaped like the hollow. So lots and lots and lots of electric motors parts are made by casting, steel or aluminum usually. And as a result of working in electric motor tech and building factories, we had to learn a lot about casting. So much casting. So the problem with casting is it takes a lot of tooling, there's a lot of lead time, it's very painful to change, and it's not a very flexible process, and it can be quite hazardous. You got to be very careful with it. So wonderful for mass production if you're doing the same thing every day. So car manufacturers have a lot of success with casting. They're making the same thing over and over and over again every 15 or 30 seconds maybe. But when you're making stuff in a slightly lower volume and you've got a lot of part mix, like electric motors, everything's a bit different. The front's a bit different, the size is a bit different. You're having to cast different things all the time, and it was a big problem. So this was a big part of our life was dealing with this problem. So at the time, this is sort of 2013, we thought metal 3D printing looked like the answer. So I've made a lovely fake AI image here of what we thought might exist, which is a big box, and you just tell it what you want, and out comes the stuff on a conveyor belt. So what we were really hoping was that metal 3D printing was going that way, and we could start to replace some of the stuff we were doing with casting with a more flexible process that didn't require long tooling lead times. So we thought, let's get into this. Let's see what we can work out. So we tried it. It was very exciting. It was a lot of fun. We made a lot of prototypes. The prototypes generally worked pretty well, but it was just way too slow and way too expensive for solving normal manufacturing problems. So we're talking orders of magnitude out in terms of feasibility. So that was quite disappointing. We also noticed the parts looked pretty good. So I've got some example parts on the table there, but they weren't normal parts. They were kind of thin-walled, small. Often you had to use lattices and things. You couldn't just make a big chunky metal part like we were used to for an electric motor. So for us, it was a bit disappointing. So we thought, well, maybe there's an opportunity here, actually. So we thought, let's get into metal 3D printing. What a great idea. Here is a lovely image. So most of you probably are watching the fancy video here and not listening to me, but I'll explain anyway. This is a cross-sectional view done in a synchrotron with X-ray of a SLM style powder bed fusion process. So you're looking at a powder bed and a laser going across the top and melting that material. And in fact, you see there that it's not really a very nice process. You can see the particles jumping out, the molten globules jumping out, the powder's going everywhere. So it leads to these problems like lack of fusion and spatter inclusion, weld spatter inclusion. So this is kind of how the process works. For the very small parts with thin walls, it's pretty good actually, and indeed they're getting better at using it. 10 years later, they're getting better at using it in other applications. But this process of having to add heat until the material melted, and then wait for it to cool down, and then add more material, add heat again to incorporate it into the part. There's this kind of thermal pumping cycle. You're having to pump the material up to a liquid state, wait for it to solidify, and then add another lot of material, pump that up to a liquid state. And it just added time and it added energy. And we just noticed that that seemed to be where all the budget was going, was into this cycling between liquid and solid. So we thought this is not going to work. Like we can't develop this tech to a point where it'll suit a manufacturing problem. Physics won't let us because of this problem with the thermals. So we thought what we really need is a process that works in solid state. So can we make metal parts without melting metal? So this was really the question that we went after. So we thought, well, if melting's the issue, then let's just figure out a way to make a solid metal part without melting the material. Easy, right? So we had a look around. We thought something like powder metallurgy. So I've got a little description over here. You take a cavity, you fill it with metal powder, you press the metal powder down, and you eject this gear. Indeed, a lot of gears are made this way with powder metallurgy. I've got to be careful talking about this because I know Brad's an expert in it, and he'll bite me. But you take the metal part out, it's green, it needs to be heat treated to fully solidify and densify and shrink. But this is a way of making metal parts without melting the metal. So it is around. So what we need is something like this, but without all the tooling. So if only there was some way to combine all the powder together into a solid metal part without having to melt it. And we kind of despaired because we couldn't find the process. Although I'm sure there are many people in the audience who have a suggestion. So, not a lot of practical candidates. Ultrasonic sheet welding, explosive bonding kind of came up immediately. This is 2014. None really felt like they were going to work for a kind of a production application. So, it's a little bit complicated. So we thought, if only there was a way we could do this. Eventually, we found a really obscure reference to a thing called cold spray in this very, very old translated Russian paper. And we thought, cold spray, is that a translation error? What's this cold spray thing? So we looked around and looked around and we found out what cold spray was. And we thought, wow, this is actually the right kind of technique. Um, Interesting. We looked a bit further and we found the CSAT community and we thought, wow, this is actually something a lot of very clever people are thinking about all the time. This is wonderful. So, what we really needed to do was find this new application for it where we weren't just talking about, manual repairs, building small structures, but actually trying to build really cheap, really fast metal components. So, our hope for cold spray was that we were going to be able to deposit the metal without melting it. That's good. But if we can keep it solid, we're not going to need to melt any of that metal. Great. Let's spray it on. Let's build the part up. Sounds feasible. Okay, good. Here's where the problem came in. The problem was cold spray is a stochastic process. That's a fancy word for random. So there's a very random element to it. We're not controlling where every particle goes. We're controlling sort of a distribution of the particles. The way that the deposition method works is complex. It's a function of what you're spraying onto, what you're spraying with, velocity, temperature. There's quite a lot going on there. It was solid state, but this whole idea of just being able to generate layer upon layer and stack them up was not really something that cold spray did. Cold spray liked to taper in. It liked to decrease in kind of layer area with every succeeding layer. And so we thought, right, we've got some work to do here. So the good news was we were already people expert in real-time control, manufacturing, robotics, control systems, all that mathematical stuff. So we thought maybe there's a way to do this. We looked around quite hard. We didn't find anyone who seemed to have cracked this yet, but we were pretty determined. So there's another artist's rendering of kind of our crazy idea. Let's take a robot. Let's automate the robot. Let's put a cold spray nozzle in there and let's have the robot generate the geometry repeatably and reliably. But that turned out to be quite a challenge. So really, when you think about it, you're trying to take these little tiny splats, which have this distribution, in a circular pattern, and you're trying to turn that into a repeatable construct, a repeatable geometry, by automating the process kind of really exquisitely. And indeed, that turned out to be quite hard. So we worked out we needed to automate really every part of the process. We needed to manage every part of the process, control variabilities. The business of manufacturing really is about controlling variabilities, understanding where things can be allowed to vary because it might be cheaper or more convenient, and where you need to control them or you're not going to get the outcome you want. That's really the science of manufacturing. So we applied those same techniques to cold spray, and we spent a long time thinking that this wasn't going to be possible, actually. But nevertheless, we persisted. This was a very difficult process. So we worked out that we had to build everything at once. We had to build the machine, we had to build the nozzle, we had to build the robotics, we had to build the software, all the automation for controlling everything safely. We had to build all the simulation tools, all the compensation tools, all that real-time control. And really, we had to do all this simultaneously in order to get that predictable, reliable outcome that would allow us to be able to deterministically manufacture something every time we wanted to. So There was a lot to control. Fortunately, we had a very good team, and this was kind of our background, was working in these very kind of multi-physics type problems. So what you can see here is a one of our very first printers. We call this one Blackbird. We've still got the prototype in our office. Anyone who comes to our office will show it to you. It didn't work. It was missing some very important features that we worked out we needed, but we learned a lot. We learned what we needed to know by doing a lot of work with that system. So in our old office, we had this wall. It's actually it was about probably 20 feet long. We're just showing a small section of it here, the wall of failures. So trying to automate cold spray led to a lot of very interesting shapes. So as I'm sure those of you I'm sure we have a lot of people on this call who are expert in manual cold spray and know about how to generate geometries. Like my hats off to you guys. This is a process that's not particularly intuitive, I think, and it's a real skill to be able to do that work. It's not like painting, which is relatively straightforward. You're just essentially making a two-dimensional sheet. Cold spray, what you're putting down depends on what's already there. And it's quite complicated, actually, to predictably make something. So we had some fantastic looking parts. They weren't useful parts, but we had parts that looked like they'd been eaten by termites. We had parts with spikes and growths all over them. And indeed, we had to work out why that was happening, establish controls, and spend a lot of time iteratively developing those automation processes so that irrespective of what geometry was being thrown at the system, we didn't have those kinds of failures. So there's a huge amount of work, a huge amount of labor and effort in this. So this was our first big success, 2016. It's a cube. So it's a pretty kind of unimpressive, ugly little cube. It's only a centimeter, so it's about a half an inch to a side. But the walls are flat and they're at 90 degrees to each other, and indeed it has edges. And the edges are relatively sharp. So it was a crazy amount of work getting to the point where we could make this ugly little cube, but we were very, very proud of it. So most importantly, we could make that same cube over again. We figured out how to make the top flatter. And indeed, if we wanted to make another one, it would look just like this one. And if we wanted to make a larger one, we could do so without kind of knowing how to do it in advance. Our automation would allow us to do that. So that was our first big success, probably about 10 years ago, as we sit now. So there you go. And it was tin, of course, because our prototype nozzles that were running in our garage were very low energy. So tin, you can just about sneeze tin together. It really doesn't need a high velocity. All right. And about a year later, we brought out our first product, Lightspeed. So some of you know this product well. So this will make parts up to about 10 pounds. And this was us taking all of that tech, compacting it into an artifact and wrapping it up in a way where people could easily engage with it. So indeed, you could take a part that largely the process had never seen before, and if it met the design rules, you could print it fairly quickly. So why could you do that? Because of all the automation. The automation is really what allows you to do that. So generally, here's how the process works. So our objective function is to compact the time from need to the part being available as much as possible. So that includes the design time, the setup time, kind of project time, as it were, the printing time, but also the machining time, the heat treatment time. So generally, we heat treat and machine every part that gets made with our process. So indeed, you can see on the left there is the design and sim time. So this is where the automation really shines, is you can take geometry that you have, check it against the design rules, modify it if necessary, work out which orientation you want to print it in, and really the automation kind of takes over from there. So I'll explain a little more as we go. Then you print it. So we don't generally have laboratories with, broken, half-built 3D printed parts everywhere. If any of you have been to a 3D printing lab, you'll see that's how it usually is. We would normally produce those in simulation. So indeed, that green part you see there is a simulation, which should be quite geometrically accurate compared to the actual part that gets printed. So we print that, we stick it into a furnace, we cook it to improve the alloy, very much like you would do with powder metallurgy, and then we finish it with machining. So indeed, with our new high pressure systems, which you'll hear a little bit more about at CSAT, we don't need to heat treat as often, but many of our alloy systems work extremely well with heat treatment, and usually that's the right answer. So let's talk about TwinSpeed. TwinSpeed is the name of our software. So those of you that have our system will know TwinSpeed well. It's really our kind of PC software that allows you to manage the workflow for the printer. So you would do all your part locating, and you would do all of your simulation with TwinSpeed. So we have two primary workflows there. One is for printing, where you take a geometry that doesn't exist and then you make it exist with TwinSpeed. Or in fact, you can take a substrate geometry, which is usually just a flat plate, add the part you want to be on top, and then have it generate that part. So the substrate doesn't actually have to be flat. The substrate can be a part already, and you can make another part joined to it. TwinSpeed doesn't really care. Separately, we have a coating workflow. So when we say coating, this is, again, it's not really the same thing that you would normally do, manually, for example, with a cold spray nozzle. So with coating, we would normally take a shape that already exists, which can be a fairly sophisticated three-dimensional shape, and we can use the printer to apply a coating automatically, like paint that surface to a kind of given thickness. So we don't use that workflow as often as I think is justified, but nevertheless, it's something that the software does, and it does solve an interesting set of problems to be able to automatically paint like that. All right, here's kind of our language. So if you're using our software, we've got a substrate holder, which mounts to the robot. That's that yellow piece at the bottom there. We've got a substrate, which is usually just an aluminium laser cut plate or water jet cut plate. It's generally sacrificial. You can reuse them. The parts break away fairly easily, but often it's a good idea to use fresh ones. You would bolt the substrate to the substrate holder, and indeed you would print the part on top of the substrate. So when we talk about terms, that's what we mean by substrate holder, substrate part. This is the language. So yeah, interestingly, the substrate is part of the process. So it can be a plate. It doesn't have to be a plate. So for example, if you had a small statue of a dog and you wanted to print a hat on top of that dog, maybe in a different material, you could use that. You could do that by bringing the dog in as a substrate and then adding the hat on top, and it would automate that workflow for you. So in this case, in the image, I've used the actual diagrams from our manual, by the way. So that's where the figure 34 comes from. It's from our TwinSpeed manual. So we can take there's a fixture there. We've added that pipe, and we've masked out where we want to coat that pipe. And indeed, that'll automatically apply a coating of whatever material is loaded to the controlled thickness on top of that stock there. We also have automated design rule checking. So there are design rules. We have a document in the manual that talks about what kind of geometry is allowable. As you build up, what angle can you build outwards at? Because if you're building up and you're building very close with a tiny gap flat to the substrate, that would be very difficult to do. You'd need to get the nozzle around behind the substrate to achieve that, which causes an occlusion issue. So what's the process for building that part up, and indeed, where are their limitations? So sometimes it's difficult to intuitively tell where in your geometry there might be a limitation. So we've built automation into TwinSpeed directly, which will do design rule checks and then highlight the areas of the component where there is a design rule failure, and you can change the geometry prior to printing just to ensure that it does print properly. So in this case here, you can see there's a little H-shaped piece, and that thin section in the middle is too thin. It's slimmer in thickness than the spot size of the material from the nozzle. So that geometry is unprintable as it is, and it's warning you about that. That's what you can see in that picture. So let's talk a little bit about the toolpathing work. So really, toolpathing is the main job for TwinSpeed, is to figure out automatically how the robot should move to generate the part that you want. So I've just got a little example here. So top left, you can see we've taken a substrate, we've brought our CAD model in. In this case, it's of an Aussie Shepherd. So this is a genuine part that we made recently. Someone was leaving who used to bring their dog in regularly, so we made a statue of their dog for them. So that blue geometry there is straight from the CAD. The print simulation, so we would understand how to decompose that part automatically, build the toolpath, and then simulate what that toolpath actually did, generate the geometry. That's the green. So in fact, that's exportable. So if you have a machining operation afterwards, you can take that geometry that exists and you can bring it out into as stock into your CNC machining process and plan that out while the part is printing. So that happens very often in the field. That's what the green is the simulation. Bottom left, you can see there's a copper dog statue that's been printed, which matches that green simulation quite closely. It's a slightly different angle, but it does indeed match. And then, of course, we've got the reference design down there at the bottom right. So, yeah, the simulation turns out to be quite an important part of the process. So, the real challenge here is most of the time, our technology is asked to make a part that already existed before. So, for example, we're making a fitting or a coupling or a bracket or something, some sort of armored vehicle component. And the people who originally designed that component wanted to solve a particular problem, and they had certain manufacturing tools at their disposal, which were not cold spray. So we have to re-engineer that part. We have to solve the same problem, but we have to switch to a cold spray manufacturing process in order to make that part. And the people who originally thought of the part didn't have that same constraint. So we need to solve the problem, generate the new geometry that's cold spray printable that solves the problem. And the simulation is really useful from a point of view of, it's a very complex, intractable problem. What's printable? We've got all this, real world problem to solve. And indeed, tracking what's printable and what's not beyond intuition is very difficult. So having the software deal with that for you is quite helpful. So the print preview tool, essentially the simulation, is kind of a what you see is what you get. So you can very quickly say, what if we tried this? Does that part simulate in the way I expected? If I were to have that in my hand, could I solve the problem that's in front of me? So most metal 3D printing processes don't have that print preview, which to me just seems off. If you really want your metal 3D printing process to be helpful, you should be able to predict and tell people what it might do, just as you would with, like a word processing package. So really, it's all about generating the answer to that problem very quickly. So you'll see also in the top view there that blue hand, the original CAD, is a lot more detailed. This is a very small part. It's only about this large, and indeed, the resolution of the nozzle is limited by the inside bore of the barrel. So that spot size of printing, and this is right on the edge of what's really printable with that size nozzle. But you can see down the bottom there, it's done a pretty good job replicating that geometry, but it's not exact. And our automation process in general tries to overbuild the part. It tries to make sure there's more material there than needed, because we know once it's printed, taking some material off is relatively easy. Adding more is not easy. So we bias it in that direction. It doesn't always get it right, but that's where we bias it. So the simulated parts can actually be compared very directly with printed parts. The simulation process, again, isn't perfect, but most of the time it's an exceptional guidance for the real part. So, we've taken you can see a figure here of several different coating plate processes being applied and what the simulation looks like. We've actually found one of the most useful avenues for this process is learning, being able to try, experiment, observe what happens when you try and generate a particular geometry, and indeed learn about how to solve your problem better without having to turn the system on, print the material, wait for things to be done, etc. So the automation really is covering a lot of ground here. So when you think about what's actually going on in the printer, so in this case, the nozzle is stationary for this printer and the parts moving around. For our warp speed and X speed printer, that's how it works. For our very large format Titan printer, it's the other way around. The nozzle moves and the printer is stationary. But the automation has to deal with, okay, let's make the geometry. All right, that's step one. Let's make sure the geometry can be knitted together as intended. But we've also got to account for all of those joints in the robot. How do we get all those joints in the right position so we end up in the right place? We're not tying the robot up in knots. We're not driving it into blind alleys. And how do we deal with things like collision? Collision is actually a very complex issue for an additive manufacturing machine because you're literally adding material. The system can collide with the material that it's added and destroy itself. Indeed, during prototyping, this happened to us a few times. So you think about something like a FDM printer, polymer printer. If you have a look, you'll see it's building up the material very carefully in layers so the nozzle doesn't crash into the part. The nozzle's always got clearance. In this case, that's not necessarily true because we have a 6 degree of freedom robot. It's quite possible to get that robot to crash into anywhere in the printer, essentially at any time. So we've got to manage that issue of collision as the part's building up. So there's quite a lot going on under the hood, as it were. All right, talking about geometry, it's hard to build. So we have a process called automated build planning. So in the case of the hand there, you can see that little inset picture, the hand's split up into different colors. Every one of those colors is subject to a different build plan. So the system will kind of reorient itself in space, set up a new kind of datum and build up at a different angle. That's all done by automation. So we've also got section analysis. So you can see we're sweeping through there. And indeed, you can see the different colors of those different build paths within that green. And in fact, you can also see when it resets that there are a few sections here where the simulation is still lower. The underlying geometry is still showing through. So section analysis is incredibly helpful when you consider you're in the moment, you haven't got a lot of time, you've got to solve a problem. What is it I'm looking at and where indeed might it be a problem for me later? Being able to do that live sectioning is very helpful. All right, our next element here is harmonica. Harmonica is a code name for our user interface. So this is what you see on the printer itself. So we set it up to be three-dimensional, high refresh rate, very visually appealing, really just to make life easy when you're in the field. So I've done a lot of work in the field. You're being attacked by insects, it's hot, you're incredibly sweaty, you're tired, maybe you're working under a red light. You really want the cognitive part of your job to be simple. You have a lot to worry about. So having that very well-designed user interface, very visual, very easy to get right, is quite important. So we call this part of the system harmonica. So down the bottom there, you can see where it's located on an X speed. So we will have one of our X speed printers on display, I believe, at CSAT this year. So you'll get to see the whole process in action if you're at CSAT. So let's talk a little about the use of technology. So technology really only matters when it solves a real problem. So I've got this innovation adoption curve or a technology maturity curve on the left here. This is off of Wikipedia. There's a page on this if anyone's interested. This is the distribution of people in the world. And indeed, the people who love innovation is about 2.5%, 1 in 40, and 39 in 40 hate innovation. So this is important to remember when you're trying to convince people to work with a new tech, is that most people don't like that change. So the tech itself doesn't really have value to people. People need the tech to solve a problem, and the solution has value to people. So there's a subtlety here that's important to know. So if we're talking about automation for cold spray, we really need to find those people whose problem it will solve. And in our case, it's urgent access to metal parts. So just as an example, I like tech. I'm one of the 2.5% of people. I would adopt tech even if I didn't think it solved a problem yet. Most people are not like me. So example would be horses. I quite like horses. I think horses are very interesting. I would never own a horse. I would probably ride a horse. I quite like being around them, but owning one is not for me. So I'm in the 39 in 40 for horses, but the 1 in 40 for tech. So yeah, most people want the outcome. So there's a picture of us out in the field. You can see what the environment's like where we're typically working. So the people that we're working with really don't care about cold spray at all. They care more about rapid part manufacturing, but what they really care about is being able to avoid downtime and loss. So solving that problem for them is the real answer. So cold spray is a central part of what we're doing to deliver that for them, but it's not everything. Their automation actually is the part that they see and experience and value in the work that we do with them. So by comparison, cold spray repair, most people at CSAT are there for cold spray repair, cold spray coating. This is actually a totally different beast to what we do. So this is a fantastic thing. Whenever I see this picture of the S92 VIX work, I believe I'm very impressed. But this is not what we do. Our system doesn't know how to commence surgery on that part, doesn't know how to prepare it, and indeed wouldn't be able to generate a custom restore like a manual operator with experience would be able to do. It's simply a different task. So for reference, this is not what SPEE3D does. We don't work in this industry. What we do is go out with people who have limitations, who really need parts, and we provide them with a system that allows them to rapidly generate parts. So there aren't too many people in that industry who are excited about cold spray. We are. What they are excited about is the automated manufacturing. So automation changes the answer. Really, it's about removing the burden of the operator. So the human's job is to work out what should be done. So that might change in the future, but right now, which part do we need? What's the priority order? And how quickly do we want it versus maybe how high a quality do we need the outcome to be? These are the kinds of decisions a human would make. A human understands the operational requirements. They will understand why you would do something. Second point, our software and automation does all of that complex planning to create the part. So the how of the process is all done by that automation. So the person doesn't have to carry that load around with them, which in the field is very, very important. They simply need to understand what the nature of the problem is they need to solve and have the automation deal with the project element of it automatically and quickly. So this really is a solution for those problems where the project type process would be too slow. So here's an example. We did this in Reptex down in San Diego in, I believe, 2022. So this is a valve body. It's about this yay big, about 12 inches, I guess, left to right, maybe a little bigger. So it was quite a hard challenge. They essentially said, we put the system on a ship. We're going to pretend that the ship's been hit by a torpedo and that the seawater extraction system that would otherwise be venting the seawater from the hull is failed. And there's a part that you need to generate within 4 hours or the ship will sink. And we thought that was pretty tough, but that was what they wanted to try. They wouldn't give us the part in advance, so they started the timer and they gave us this valve body design, and we were able to generate that within 4 hours on the ship. So printing, heat treating, machining, pressure testing, all on board the ship. So yeah, that was I'm not going to tell you that was fun. That was quite a stretch to be able to do that. But being able to do that is a new thing. Creating a custom part to save a sinking ship that you didn't know you needed before the ship was torpedoed. I think that's a new thing that didn't exist before, but we were able to demonstrate that we could do that now. So there's a range of parts that we produced during that trial. There's me holding up one of the parts to a very excited looking crew. So yeah, what did we do? The automation meant that we could solve the problems that were coming quick enough for it to be relevant, quick enough for it to be important. The software and mathematics really did all the heavy lifting for us. So if we hadn't had that, even if we'd had our very best people there and they'd had all the coffee in the world, we wouldn't have been able to solve those problems in a period of time that was important to solve the problem. Here's a second example. This is a tool we built for a platform called HIMARS. This is in Australia, very, very remote part of Australia. So there's a tool that's used to, I believe it's used to lock the wheel hubs on a wheeled HIMARS. It broke in the field. This was a critical demonstration, very first HIMARS in Australia being demonstrated to the Australian government. And embarrassingly, that tool failed. It's got a nasty cast iron material. It was very brittle. And it had a checkered history. And the first time I tried to use it, it broke. And without that, there was quite a lot riding on this test. And so people came and found us and said, drop what you're doing and do this instead. And we were able to produce that replacement part. So here's where that was, the Bradshaw training area, 400 miles to the nearest Burger King, just to give you a reference. Another reference, in Australia, Burger King is called Hungry Jack's. Anyway, there's a long story there, but we do have Burger King. It's just not called Burger King. So 400 miles drive to get to there. This was really remote. It was right in the middle of nowhere. And this platform had a problem. It wasn't a big problem, but it was stopping the platform from working. So we made that part, and because we were there, because we could make the part, there was a big impact. And indeed, Australia now has the HIMARS platform and uses it as part of its defence strategy. So that was announced in the national news. Nobody heard our part of that story, but now you guys have. So there you go. So here's where we were. That's literally the overhead photograph of us making that part. So yeah, without the automation, we wouldn't have been able to solve that within the time period that was important. It would have been days or weeks to solve that problem otherwise. With our automation, because that was there ready to go and we could automate the task of manufacturing that part, we were able to solve the problem in a way that mattered. So yeah, this was a really austere environment. You want to talk about austere environments. I mean, this was like Death Valley. This was hot and uncomfortable. That sand on the ground was like talcum powder. You would arrive in your vehicle and you'd hit the side of the vehicle, and 100 pounds of dust would just collapse off of your vehicle. Very, very tough environment. That was where we solved that problem for the HIMARS. So this is what we do. SPEE3D does automatic part manufacturing. So it's 3D printing, sure, but it's maybe a little more than that, because we have this very high degree of ruggedness and automation so that we can solve real problems in the moment. And indeed, cold spray is a very important part of that. But for us, cold spray is just part of it. It's just a part of the integration. So yeah, that's SPEE3D in a nutshell. Does anyone have any questions?
Steve, thanks for another awesome presentation. There are indeed a handful of questions. We actually had one come through the chat, and then I have a couple prelim ones from earlier. So I think we're going to have enough time here to knock through most of them. So I'll just start rattling them off.
Sure.
The first one that came through was, how do you see titanium cold spray particularly evolving over the next couple of years? They actually said 3 to 5, but I'm kind of curious in the 1 to 5 spectrum here. And probably in that context, give specific to how you all at SPEE3D look at titanium cold spray.
Yeah, this is a really good question. I suspect I'm feeling the same sort of frustration that a lot of people are feeling here. So as you outed me, Brad, I'm nearly got a PhD in metallurgy. So kind of as a metallurgist, titanium is an awesome material. It's really seems to me like it's underserviced in the world. I suspect, like broadly speaking, people are a little afraid of titanium because, you can't cast it easily. If you heat it up enough, it'll just burn in atmosphere, or worse. So that's kind of made it beyond the reach of simple processing. You've got to use modern processes to deal with it. And so as a result of that, not many people have engaged with it. Only where you really have to have people done that. So cold spray certainly offers an avenue to make it much easier to process titanium. We've certainly played with it. Cold sprayed titanium is just fantastic. Like, it's the way titanium should be produced, is with cold spray. I'm sure there are people in the room that agree with me. It's just a natural fit and you get a fantastic result. The challenge I have is finding applications for it. So I know there's a lot of probably a lot of people on the call even who have applications for titanium, but justifying all that effort, finding the processes to build and qualify the manufacturing system for certain kinds of titanium, we just haven't been able to justify that yet. If anybody wants to talk to us about that, of course, we'd love to talk about that. But I think there might be opportunities for working in the field. In the field, you have more flexibility, and indeed, titanium is one of those materials that could be kind of general purpose in the field. You could replace, for example, complex steel parts with titanium. I'm sure most people would be happy to sign those off, once they'd met the properties. And titanium would achieve those required properties. So yeah, I don't have a strong answer there. I'd love to look at it. I think it's a fantastic option, but I just have not hit that commercial level of saturation where we've pushed hard in titanium.
Yeah, I totally understand, and I feel your pain and resonate with the message there.
Yeah.
Okay, next question actually kind of threads into that pretty nicely. It's a qualification question. So where is cold spray and where is cold spray additive manufacturing with regards to your more classical qualification schemes here and the individual
Yeah.
listed MQ, OQ, IQ, and PQ, which are kind of U.S. Department of Defense or I guess U.S. quality oriented ideas. I don't know if you know what those are, but maybe talk about that generally so that the
Yeah.
entire constituency here can understand the answer.
Yeah, sure. So let's talk about I suspect what we all really mean here is risk management. So qualification, certification, validation, these are all risk management words. So we want to be able to make the part, but we also want to be certain that the part is fit for use in a way where we're not negligent for having used the process. So, the oil and gas industry's got their own way of thinking about this. The medical people do, the aerospace people do. Um, this whole process of risk management is fascinating. Now, additive manufacturing in general is really suffering in this space. So you see pockets here and there. So, indeed, ASTM is about to fly me to one of their events just to talk about this issue. They're struggling with it as much as anyone, I'd say. Um, how do you get to a point where you can be certain that a one-off additively manufactured part hits a kind of a known level of risk management? So I don't think anyone's particularly solved this well yet. So cold spray additive, we've got approvals here and there to do this and that, but there's no such thing as a standardized risk framework that the oil and gas people and the aerospace people, everyone, they all subscribe to and will all accept. They've all got their own systems. And so I guess a lot of people on this call will be defense related. And of course, defense, NAVSEA, for example, have their own system again. So one of the key problems here is when you're making parts in a production sense. So remember, my background is manufacturing engineering, amongst other things. Manufacturing engineering is all about statistics. So you produce, a million items. How many parts per million? 2,000 is a good number. Didn't meet your quality spec. So you can only get that level of data by just having this incredibly dense data set generated across a million parts. When you do that, though, you end up with a high degree of confidence in what the part can do because your data set is statistically relevant. So this is how they do things like drug studies to observe, whether a drug is safe for human consumption. It's all done statistically because they're very complex systems, and you just get the data and you measure the statistics of it. So when you're doing additive, though, often, especially in our case, you want to make one. So we might not even make a trial piece. People will say, I have this urgent problem. In 4 hours' time, I need this ship to not sink. Come up with the design, produce it. The idea of a quality system in that case is a very, very different idea because you can't destructively test, for example, if the entire production batch is one piece. You've got to do only non-destructive testing. And so you've got to have a lot blueprinted and mapped out in advance. So NASA have a relatively healthy thinking on this in their 60/30 standard. So NASA 6030, if anyone's in this field and they're interested, they can go and look that up. They have this idea of producing very small batches and building just enough statistics to be flight ready with additive tech. But the kind of bureaucracy technology is still evolving. This business of risk management is still evolving, and all these disparate groups are busy thinking about it on their own, and no one's yet kind of come together to say, actually, this is all the same problem. Let's solve it once. So I wish I had a healthier answer, but that's kind of where the world is.
I think we all feel that pain, and I don't think anyone would disagree with you.
Yeah. So I mean, the answer's there, but we've just got to get the bureaucracy to put the time in, I think.
Yeah, and the money,
Yeah, indeed.
it's not
Yeah.
cheap.
Yeah. Certainty is not free.
Mm-hmm. So I have a follow-on question going, I guess, further down that train since you mentioned NDE. How far, I guess, upstream and downstream into processes have you all looked at automation, right? Have you looked at or thought about, can I automate the heat treatment? Can I automate the machining? Can I automate the inspection? Are there tiebacks with the great simulation capabilities you guys have and deep understanding of the construction of the part to NDE inspection where you know or already have very good indications of where to look at a part for defects to simplify those processes to be more convincing in the qualification or I guess ascription of performance to a part that's a one-off, for instance?
Yeah, these are all fantastic ideas. So we have done bits and pieces of these things in a prototype sense, especially the CNC machine integration. That feels like that's quite important, is adding more automation to that. I mean, it still astounds me that for those of you that know CNC machining, quite how manual a lot of those processes still are. I mean, CNC machines, largely the ones that run G-code, they're effectively running on punched paper cards. Like the technology really hasn't improved that much since those times. Of course, there are specific ecosystems from specific manufacturers that are much better than that. But the idea of kind of working purely graphically and then having a CNC machine automate the whole manufacturing process, I don't think anyone's really done that. So that might be something we look at if we see enough demand for that. I think that's important to do. The heat treatment as well would certainly benefit from automation. So I think once there are enough people that see the value of having a lot of automatically generated, OQE, objective quality evidence, that sensor data, the kind of the all of the digital twin processing data that comes out of printing, heat treating, machining. There's a body of people growing that are interested in that data and can see the value of it and can turn that into artifacts that the bureaucracy can understand. So I think that's happening. We can't afford to get too far ahead of where people are with the tech, or otherwise we're just adding training burden to people that don't understand. We're adding complexity to people's lives that they don't really have the value of. So we've kind of got to evolve those things as the community engages with them, and we've got to make sure we're very compatible with where people are. But yeah, absolutely see the value in all that. Like the more automation largely in these manufacturing processes, the better. Wherever you can use a pocket calculator to solve a problem reliably, like that's what you should do, right? And this is kind of that same argument writ large.
Yep. All right, I'm going to pivot a little bit here. We have a question from Rosebank. They're actually asking more specifically about the Australian market, but I'm hoping you might actually be able to generalize this to the global markets. Where do you see cold spray integrating into civilian and commercial aerospace? Oh, and they actually said the Australian market overall. I made up aerospace.
Yeah.
So where do you see cold spray integrating into civilian and commercial markets? And what do you believe the big obstacles are for that integration?
All right. Well, hey, Rosebank, hope you guys are doing well. Looking forward to catching up with you again soon. So yeah, this is an interesting one. So we don't do a lot of work in Australia in aviation, but just speaking philosophically, maybe, as you said, Brad, a little more globally. Um, there are kind of two jobs for a manufacturing tech. So let's treat repair as a manufacturing process for the moment. So repair and manufacturing, I guess, is what I mean. So you've got the kind of primary production point where you're making the thing for the first time, and then you've got the repair and maintenance points that happen later down the track where maybe you're making parts and maybe you're repairing parts and maybe you're, improving parts, adding newer designs of coatings, for example. Um, Aerospace, I think, is interesting because uh, you know, we're so constrained for materials typically for aircraft. So, materials like 2000 series aluminums for the skin, and 7000s often for the structural components, and 17.4 stainless steels for the landing, for the high shock landing stuff. Like, we don't really have a lot of option because there's so much weight constraint in an aircraft. And so what happens is some of the secondary objectives, like corrosion and lifetime performance, get pushed back in favor of more cost, weight driven type objectives. So aircraft just seem to be fragile things. If they were a creature, they'd be fragile. I mean, birds are fragile. So they've got a lot to do with a small amount of mass. So the corrosion element seems like it's probably the primary driver. So, all of Vic and ARL's work over the years, a lot corrosion's been a primary driver. It's all about understanding where the atmosphere, water, salt has impinged on those very sensitive alloys and made them unworkable, and you can regenerate them. So cold spray just does that so well. Like, cold spray repair just seems to me like an absolute gimme. And aerospace is the place where all of that need. I mean, ARL done a lot of work in aerospace for that reason, right? That's where the applications are more obvious, particularly in terms of like payback and return. So I think commercial should should really be looking at this. I mean, they're all struggling with a fuel price right now. Maybe they should be looking at opportunities for reducing their maintenance overhead. And cold spray seems like it's perfect. I mean, Rosebank seems like they're in a perfect position to look at that. But of course, the bureaucrats and the risk management people need to be satisfied. So, bureaucratic technology needs to improve, perhaps, to solve this one.
Awesome. Well, Steve, we're bumping up on time here, and I don't want to run over. So thank you very much for another fantastic presentation. Actually, a quick call out and a reminder to everybody that there will actually be an XSPEED at CSAT this year. So you'll get to actually see one of these machines live. And again, that's June 9th through June 11th in Worcester. If you have not signed up yet, please do so. And we look forward to seeing Steve and the XSPEED at CSAT. Thanks so much for your time, everybody.
Thanks, everyone. See you soon.